Hi, everybody. Today we're going to be working on question 3 of the Winter 22 final exam. All right. So this question is asking us about pipeline performance. So it gives us an example LC2K assembly program, and it gives us I'm not going to do this in red. It gives us the relative percentages of each of the instructions. It also gives us that 60% of the branches are taken, 20% of R-type instructions are followed, and then 80% of load instructions are followed by an immediate dependent. Okay. So it first asks us, what is the CPI of a program when the processor uses detect and stall and speculate and squash? So the way the detect and stall method works for resolving data hazards is every time we see that there's a data hazard, instead of forwarding or doing anything in the instruction fetch stage, we simply insert a stall. As far as which instructions this applies to, this is going to apply to load R-type instructions, load and R-type instructions, so loads, adds, and NORs. And so using detect and stall in the 5-stage LC2K pipeline, we have 2 stalls for each of these. So then we are using speculate and squash for control hazards. So speculate and squash is the resolution technique that we use, where we guess whether something is going to be taken or not taken. If we're correct, then there's no stalls that are inserted. And if we're incorrect, then we have to replace all of the instructions that we assumed we would execute with no ops. And so in the case of the LC2K 5-stage data path, we have to insert 3. So when we're calculating CPI, the way I go about it is the CPI for at least pipeline data paths is I initially assume that the CPI is 1 because each instruction is going to take at least 1 cycle to execute. So then from there, we can consider how many of our instructions have hazards. So let's first consider data hazards. So we'll do that in green. So data hazards come from R-tape and load instructions having dependent instructions after them. When we're using detect and stall, we insert 2 stalls or 2 no ops for every single data hazard. So the question kind of here is, how many data hazards do we have? Well, it says 50%, so 0.5, of our R-type instructions, of our instructions are R-type instructions, and of that 50%, 0.2 of them are followed directly by a data hazard. Additionally, it says 25% of our instructions are load instructions, and of that 25%, 80% of those are considered to have an immediate dependent. So if we add these up, this gives us the total proportion of data hazards. And if we multiply it by 2, that gives us the weighted, the amount that this will affect the CPI. So that 2 represents the 2 no ops using the detect and stall method. So then looking at the control hazards, so control hazards are affected by branching. So we're going to only look at the BEQ instruction. And we see that 15% of our instructions are BEQ. So whenever we mispredict, right, we are going to insert 3 no ops. And so now we need to consider how often we're going to have that. So 15% of our instructions are branch instructions. And then of that 15%, we need to consider how many times we're going to be incorrect. So our branch predictor is predicting not taken. And so basically, we need to consider how frequently we are going to take the branch. Well, it says that 60% of the branches are not taken, which means that 40% of them are taken. And so 40% of the time, we are going to be incorrect. And so we need to account for that. And so if we multiply that out, I'm going to do some mental math. That gives us 1.0 plus 0.4, no, 0.2 plus 0.1. So 2 times 0.3 plus, that'll give us 0.06. So 3 times 0.06. And if we add that all up, that should give us 1.78. Okay. So then we are looking, it asks us, what is the CPI of the program when the processor uses detect and forward for data hazards and speculate and squash for control hazards? Okay, so with detect and forward, what we do is we try to forward data through the pipeline to reduce the number of no-ops, or the number of stalls that we have to insert. And and so this is actually different depending on the type of instruction that we're executing. If we have an R-type instruction for detect and forward, with the 5-stage pipeline, we only have to insert 1 no-op. And with load instructions, we have to insert 2 no-ops. And so we are still using, you'll notice that we're still using speculate and squash with speculate not taken. And so what that means is that this value, we can kind of just copy down here. And we can also copy that down. And so our CPI is equal to 1.0 plus, we're going to recalculate the data hazards, but the control hazards are still going to be 0.18. So that's this number. Okay. So now we need to recalculate the data hazard. So we need to consider 2 situations, the R-type instructions and the load instructions. So doing the R-type instructions first, we have 50% R-type instructions, and of those R-type instructions, 20% of them are followed by dependents. But this time, instead of inserting 2, we're going to insert 0. So we actually don't need to even consider the R-type instructions, right? We only need to consider the load instructions, which will have 1 no-op, right, when we're doing forwarding. And so we just do 1 times, I'll switch back to green. We do 1 times, and then the frequency of these load dependent instructions. So once again, it's going to be 0.25 for our 25% load instructions, and 80% of these are have dependencies. So we have that. And so this number will give us 0.2. And so 1 plus 0.2 plus 0.18 gives us 1.38. Awesome. So now moving on to the last part. It asks us, given that the processor frequency is 1 megahertz and the program executes 1 million instructions, how many seconds faster is the execution time for a program when using detect and forward? So the way that we calculate execution time is we take the CPI and we multiply it by the number of instructions, and then we multiply that by the frequency. So the frequency is essentially how many instructions can you execute. So essentially we want the time over number of instructions, right? And so when we're dealing with 1 megahertz, right, that tells us that we are executing 1 million instructions per second. And we're always going to be executing 1 million instructions, right? And we're multiplying that by CPI, right? And so before we even like calculate the amount of time that it would execute for either, what I can kind of do preliminarily is cross those out and basically say that the amount of time that each process or that each program is going to execute, or the program is going to execute on each processor, is going to be the CPI number of seconds, right? So on our first processor, right, we had a cache, we had a CPI of 1.78, so it's going to take 1.78 seconds on processor A, and on processor B, it's going to take, we calculated as 1.38, it's going to take 1.38 seconds. And then it's asking us essentially to find the difference between the two, and we can just subtract them, and we get 0.4 seconds. I think that's the entirety of this question. Do I have any follow-up questions? Going once, going twice, and sold. Okay.